The most advanced engine works in England is run by a man who started as a blacksmith's apprentice. This is important to understand, not because it's a rags to riches story. Those are cheap, sentimental, and usually simplified to the point of dishonesty. It's important because Matthew Murray's hands, the hands that hold a draftsman's pencil and design engine valve gears that nobody else on earth can conceive, are the hands that once held tongs over a forge fire and shaped horseshoes. The knowledge of iron that lives in his fingers isn't theoretical, it's burnt in. And the engine works he's built in Holbeck, on the southern edge of Leeds, reflects both the theoretical ambition of an engineer and the practical intelligence of a smith. If the rivalries and innovations that powered the Industrial Revolution fascinate you, subscribe now. The story of how this foundry outpaced the most famous partnership in engineering history is just beginning. The Round Foundry gets its name from the turntable, a circular rotating platform in the center of the fitting shop, 20 feet in diameter, driven by a hand crank. Heavy engine components, frames, cylinders, beam brackets, are placed on the turntable and rotated to face different workstations arranged around the circumference. Boring mills at 12 o'clock, lathes at 3, filing benches at 6, assembly floor at 9. The component moves to the tool instead of the tool moving to the component. It sounds obvious, it is obvious to Murray. To everyone else in 1795, it's revolutionary. Most foundries are ad hoc, machines placed wherever there's space, components carried by hand between stations 50 yards apart. Murray designed the Round Foundry from a blank field on paper, arranging every machine for flow. Materials enter at the north door. Finished engines leave at the south door. Nothing moves backward.
Braithwaite works the fitting bench. Fitting is the final stage, the stage where cast and machined components are assembled into a working engine. Every bearing surface must be filed true. Every shaft must spin freely in its housing without play, looseness, or drag, tightness. Every valve must seat without leaking. The tolerances are in thousandths of an inch, the same tolerances that Maudsley pioneered at Brahma's Lockworks, applied here to machines that weigh 6 tons and must run for 20 years without major repair. Every engine is a conversation between the parts. If they don't agree, the engine shakes itself apart. Bram's job is to make the parts agree, to file and fit and adjust until the cylinder talks to the piston, and the piston talks to the connecting rod, and the rod talks to the crankshaft, and the entire assembly speaks with one voice, the smooth, rhythmic, breathing voice of a well-fitted engine. He learned this on Watt engines. The first engine he ever fitted, apprenticed at 14 working in a Leeds mill, was a Boulton Watt atmospheric engine, 20 years old, needing refurbishment. He took it apart. He felt every surface. He understood through his fingers how Watt's engineering translated into iron, how the tolerances and clearances created the breath and beat rhythm of the working engine. And now he builds engines designed to replace Watt's. Murray's engines. Better engines. More efficient, more compact, more elegant in their mechanism. And Bram, whose hands learned their skill on Watt's iron, uses that skill to assemble the machines that will make Watt's engines obsolete. His wife Nell works at Marshall's Flax Mill on Water Lane. The mill is powered by a Boulton Watt engine, installed in 1791, running for 9 years, breaking down with increasing frequency as the components wear and the tolerances that Bram respects degrade beneath the grinding hours of continuous operation. When the engine breaks, the mill stops. When the mill stops, Nell's wages stop. She comes home on breakdown days with the particular tension of a woman whose income depends on a machine she didn't build and can't repair. Bram knows why the engine breaks. He can hear it in the rhythm when he walks past the mill. A slight irregularity in the breathing, a clank where there should be a click, a vibration that means a bearing is worn and the shaft is moving in its housing by 1/100th of an inch more than it should. 1/100th of an inch. The difference between running and breaking. The difference between wages and no wages. The difference between what Bram can feel with his fingers and what the world experiences as reliability. Horace Ledger arrives at the Round Foundry on a Tuesday morning in April 1799. He doesn't look like an engineer. He looks like what he is, a solicitor's representative, carrying a leather case of documents, wearing the particular expression of a man whose job is to deliver unpleasant legal communications with professional courtesy. The Boulton Watt patent on the separate condenser expires in 1800.
14 months from now. For 25 years, this patent has given Boulton Watt exclusive rights to the technology that makes steam engines efficient. Anyone who builds a separate condenser engine without a license pays. Anyone who copies the design is sued. The patent has made Boulton Watt wealthy and has simultaneously bottlenecked engine development. No competitor can improve on the separate condenser because no competitor can legally use it. Murray has not violated the patent. His engines use alternative condenser arrangements, jet condensers, surface condensers, that achieve similar efficiency through different mechanisms. The patent covers the separate condenser specifically. Murray's condensers are integrated differently, legally distinct, functionally equivalent. Ledger doesn't agree. His documentation argues that Murray's engines achieve efficiency levels that are only possible with technology covered by the Watt patent, and that the alternative condenser arrangements are patent circumventions rather than genuine innovations. The legal term is colorable imitation, something that appears different but functions identically. Murray receives Ledger in the drawing office. Papers everywhere, models on shelves, the organized chaos of a mind that works in 3 dimensions and documents in 2. He listens, reads the documents. His face, the weathered, lined face of a self-taught man who has worked 14-hour days since he was a boy, shows no particular emotion. This is not the first legal letter. It will not be the last.
Mr. Ledger, would you like to see the foundry?
Ledger looks around the Round Foundry, and his expression changes. The turntable system, the organized workflow, the cleanliness, Murray insists. Cleanliness means precision. Grit on a bearing surface means wear. The quality of the castings, the precision of the machining, the order of the fitting shop where Bram works with his 12-inch file and his thousandths of an inch tolerances.
This is efficient.
I
More efficient than Soho.
wouldn't know. I've never been invited.
Bram demonstrates the Murray engine to Ledger, not to impress, but to prove the difference. He opens the cylinder cover, shows the bore, Wilkinson's method, the same precision boring used at Soho, shows the valve gear, Murray's own design, a hypocycloid linkage that converts rotary to approximate straight line motion without the massive rocking beam that Watt's engines require. Different mechanism, different geometry, different engineering. Ledger looks at the valve gear. He's not an engineer. He can't assess the mechanical difference, but he can see that the engine is different. Not a copy, not a colorable imitation, something new, built by a man who studied Watt's principles and then went further, not around the patent, but beyond it. The patent expires on January 1st, 1800, New Year's Day. The moment midnight strikes, every engineer in Britain is free to build separate condenser engines. The competitive advantage that Boulton Watt have held for 25 years evaporates in a second. Murray doesn't need the patent expiry. His engines already work without Watt's condenser, but the expiry removes the threat, the legal shadow that has forced him to spend money on solicitors instead of engines. Now, he can incorporate the separate condenser openly, combining it with his own innovations, the hypocycloid valve gear, the compact layout, the integrated design that eliminates the massive beam. Matthew Murray built a foundry shaped like a wheel because he believed engineering should flow, from drawing to pattern to casting to fitting, all in one circle. If you want to see how one man outpaced the most famous partnership in industrial history, subscribe. Bram assembles the first post-patent Murray engine. It's smaller than a Watt engine of equivalent power, 2/3 the size, because the hypocycloid gear eliminates the beam and the compact condenser eliminates the separate cooling system. The engine sits on a single iron base frame. Every component, cylinder, piston, valve gear, condenser, crankshaft, is accessible from the factory floor without ladders, platforms, or the engine house structures that Watt engines require. He files a bearing cap. The sound, a whisper of steel on iron, barely audible in the quiet of the fitting shop. Quiet because the foundry runs day shift. Bram works nights to avoid the heat and noise of casting. Each stroke removes 1/1000th of an inch. 10 strokes remove 1/100th. The bearing cap must sit exactly flush with the bearing housing. No gap, which allows wobble, no interference, which causes drag. The difference between flush and not flush is invisible. It's tactile. Bram checks with his fingertip, runs the pad of his index finger across the joint, feeling for the ridge or gap that means wrong.
The hypocycloid model sits on his bench. He watches it in brakes, turns the crank, watches the gear trace its straight line motion, watches the mechanism convert rotation to reciprocation with a geometric elegance that makes him forget for a moment that he's assembling a competitor's engine.
It's beautiful.
It's a valve gear, Bram.
Aye, and it's beautiful.
The Murray engine is installed at Marshall's flax mill in September 1801. The old Boulton Watt engine, 30 years old now, repaired 15 times, consuming 30% more coal than Murray's design, is shut down for the last time. The boiler cooled, the cylinder drained. The beam, which is rocked back and forth 20 times per minute for 3 decades, stops. Bram supervises the installation. His hands, the hands that learned fitting on a Watt engine, connect the Murray engine to the mill's driving shaft. The shaft that turns the spindles that spin the flax that Nell works. There's a chain of connection from Bram's fingertips, through the engine, through the shaft, through the spindle, to his wife's work. He's not building an abstract machine. He's building Nell's livelihood. The Murray engine starts on a Wednesday morning. Murray is present. Bram is at the valve. Nell is on the mill floor watching from her station, seeing the new engine breathe its first breath in the place where the old engine breathed its last. The new breath is quieter, smoother. The rhythm is different. Faster strokes, lighter action. The hypocycloid gear converting motion without the heavy rock of the Watt beam. The mill shakes less. The spindles turn more consistently. The old Watt engine is dismantled. Components carried out through the engine house door. The cylinder, the beam, the condenser, the valve gear, piece by piece, the way a body is carried from a house. Bram watches. He doesn't help dismantle it. He can't. Those are the parts he learned on, the surfaces he filed as an apprentice, the tolerances he memorized when his fingers were still learning the difference between flush and not flush. He keeps one part, a bearing cap, a small iron cover 2 inches across that he filed himself at 14 during his apprenticeship. His file marks are still on it, the particular crosshatch pattern of a boy learning to file. Not yet smooth, not yet professional, but correct. The surface is flush. Even at 14, even learning, even rough and imprecise by his current standards, the surface is flush. The bearing cap sits on his workbench at the Round Foundry, beside his 12-inch file, the old beside the new, the Watt beside the Murray. Progress isn't erasure. Murray's engine contains Watt. The separate condenser is there. Watt's innovation, freed from patent, incorporated openly. The double-acting cylinder is there. The precision boring is there. Wilkinson's method, the same method that serves both shops. Murray didn't replace Watt. He continued Watt, added to Watt, stood on Watt's shoulders and saw further. Not because he was taller, but because Watt gave him the height. Murray's Round Foundry operates for another 60 years. The hypocycloid valve gear becomes the standard for high-pressure engines. The turntable layout, the circular workflow that Murray designed from a blank field, is adopted by engineering works across Britain, and the bearing cap sits on Bram Thwaite's workbench, then on his nephew's, then on his nephew's apprentices. A small piece of Watt iron in a Murray foundry, reminding every fitter who touches it that the engine they're building today is descended from the engine that someone built yesterday. The conversation between parts. That's what Bram calls it. The cylinder talks to the piston talks to the rod talks to the crank, and the crank talks to the future, to the engine that hasn't been built yet, that will improve on Murray the way Murray improved on Watt, the way Watt improved on Newcomen. The conversation never ends. The parts just get more precise. Nell's flax mill runs without breakdown for 6 months after the Murray engine is installed. 6 months of steady wages. 6 months of reliable heat and motion, and the particular security of a machine that doesn't fail because a man with a file and 1/1000th of an inch tolerance made sure the conversation between parts never faltered. That man goes home smelling of machine oil. His wife doesn't mind.